This is a Friday Shoes production. Target today is I can simplify polynomials, found on page LA2 in the back of your book. Polynomials are algebraic expressions containing more than one monomial separated by addition or subtraction. Our book likes to show you algebra tiles to model this, so I'll use that, but I will also be doing just a simple math version of it. It says a tile that is 1 unit by 1 unit represents the integer 1. They'll be using this to represent 1 unit, or just 1. And a tile that is 1 unit by x units is represented by the variable x, and they'll be using this as a visual for that. A tile that is x units by x units represents the expression x squared. And of course they'll be using this one right here for that. And they also mentioned that red tiles with the same shapes are used to represent -1, -x, and -x squared. Many times we will put a negative or a 1 in between the negative and the x. So for instance, in this one, it'll be -1x, and -x squared, we many times write -1x squared when we're trying to simplify polynomials. Let's take a look at a model of, in this case, x squared minus 3x plus 4 using the algebra tiles. So we first have to look at the expression and change them. Any subtractions need to be changed into addition using the add-up property, or what I call shishing. So notice they've taken the x squared minus 3x plus 4 and changed the subtraction to x squared plus -3x plus 4. Then using the actual algebra tiles, you can see they have 1 of the x squareds, 3 of the negative x's, and 4 of the 1 units. And there they are. That's how you use algebra tiles. See if you can do that for these down here. So to use algebra tiles to model each polynomial, go ahead and stop the video. See if you can draw the algebra tiles that represent each one of these. Of course, I'm going to continue here. First thing we do in A is we change it to addition by shishing, add-out property, 5x plus -6. Then we would draw our pieces to that, and that would be 5 of the x rectangles and 6 of the -1 squares. Taking a look, and that's it. And then taking a look at B, we have 2 x squareds plus 4 x's and plus 3. So what we would do here is, since there is no subtraction, all we would have to do is literally draw our 2 x squareds, 4 of the x's, and 3 of the 1's. That's algebra tiles. Let's take a look at one where we're simplifying a polynomial, where we're just reorganizing, putting things together that go together. So simplify -3 plus 4x plus x squared plus x. Well, the first step is being able to draw it using the algebra tile. So we have 3 of the -1 units, and then we have 4 of the x units, 1 of the x squared units, and then another 1 of the x units there at the end. Hoping you see that those greens should be probably put together. So let's take these two and put them and organize them together. So if I do that, you'll notice we have now organized those together. We have 1x squared, we have 5 of the x's and 3 of the -1's. From there, you might notice that they have, you notice that once we organize them, we can put them down and write them in one long line fashion. Notice they've changed back the plus -3 to a -3. Don't let that confuse you. And if you see, they put the x squared first, then the 5x, then the -3. Why do they do that? Well, simplifying polynomials, it's customary to write the results in standard form. Here's standard form down here. What is that? Well, that's just writing the powers of the variable decreasing from left to right. So you'll notice they'll have x to the second power first, then x to the first power second, and then anything that doesn't, any constant, which we call something that doesn't have a variable, they'll have that last. So we just go descending order from left to right, from highest to lowest, according to the exponents. Why don't you give it a try for C and D here? Simplify each of these polynomials. It says use models if needed. I'm not going to use the models this time. I'm just actually going to show you mathematically old school way of how we did this way back in the day. All we have to do here for C is I'm going to rewrite this, make sure that that negative x actually has a negative 1x, or negative 1 put in there. And I'm going to make sure I get rid of my subtractions by shishinging. I am then going to notice that these two will go together. If I were drawing the tiles, these two would be put together. And then I know that these constants would go together. So I'm going to reorganize. So I got negative 1x. I got plus negative 2x. And then I'm going to reorganize these over here, and I'm going to have plus 1 plus 5. Once I put these together then, once they're organized, you can put them together, adding the coefficients, the fronts. So negative 1 plus negative 2 is negative 3. Put the x back on it. And then we would have our plus 1 plus 5. 1 plus 5 is 6, so it's a plus 6. So that's your final answer. It's negative 3x plus 6. That's simpler. Notice we started out with 4 terms. 1, 2, 3, 4. Now we only have 2 terms down here. Let's look at D. X squared plus, now notice I stopped myself. I'm going to try to look for any other x squareds that I see. Oh, there's 1, so I'm going to reorganize it. There's x squared. And the reason why I can do this automatically is I've already noticed that there's all plus signs here. So these plus signs, so I don't have to worry about any subtraction changing to addition. So I'm going to take and reorganize again. Let's see here. We have all the x squareds. Now I go down 1 to my x's, and that's going to be my 3x right there. So these two I put down, then I wrote down my 3x, and my final is I'm going to write down plus 4, since that's sitting by itself. Just reorganizing. Now put these two together. We've got 2 of these x squareds. Notice I don't have anything to put together with the 3x or the 4, meaning I cannot put, some people want to put these together. You can't put those together because this one has x squared, this one has just x. So you can't put those together. This is actually your final answer right there. Those have been simplified. If you do use the algebra tiles, it says when a positive tile and a negative tile of the same shape are paired, the result is called a zero pair. Remove any zero pairs when simplifying polynomials. So if you ever have a positive x squared and a negative x squared, when you put them together, they equal 0. Same with these, they equal 0 when you put them together using the addition. Let's take a look and see what happens when we pair things together here. We're simplifying 2x squared minus 3x minus x squared. Step 1 is writing the polynomial as the sum of terms. So notice they've taken the original, has 2 subtractions in it, and now they've changed it to add out property, all addition. I would like to throw a 1 right about there. So we have our negative 1x squared. Easier to use when we're counting. Now take a look what they've done here. They're visualizing this right here, saying there's 2x squareds, that's this right here. There's negative 3x's, that's right here. And of course there's negative 1x squared right there. Group the tiles with the same shape. Well, I'm hoping you can see that this goes with this. So when they reorganize, they put those together, kind of like I was doing, but without the actual tiles. When you put those two together, those equal 0. Therefore, you only have 1 of those left over. So you have 1 of those x squareds, and then you have 3 of the x, negative x rectangles. When that's done, the final answer will be x squared, or 1 of those x squareds. I like to, again, put the 1 there to show you there's 1 of these, and then, of course, there's 3 of these. Another way to write that would be x squared plus negative 3x. Either one of these will be acceptable. Why don't you give it a shot right here? Simplify each polynomial. Use the models if needed. I won't be using the models. I'll just show you how to do it, like I say, old school. Let's take a look. Let's change any subtraction to addition. So notice that's what I'm going to do here first. I'm going to to put these two together here, I can see that this x and this x go together. They both share that x. So these are what I call the same family. All right, so we'll put those together. When I put those together, and I'm starting with the x's because I know that that's going to come first. I see that 6 sitting by itself. That's going to come last. When I put negative 2x and a positive 3x together, I get a 1x result. Then, I'm done there. Then I'm going to take this and put it onto the back here. Now, you can't just put a 6 there. You have to remember, what is that 6? Is it positive or negative? What's in front of it? We never put a plus sign in front of a positive 6, but if it was negative, we would put a negative on it. This is a positive 6, so we would have to make sure that we put a plus 6 right here, not a minus 6. Final answer, if you ever look in the back of the book at a problem like this, it would probably say, here's your answer. You just simplified. You started with 3 terms, you ended up with 2 terms. There's typically no 1 in front of the x, and that is the right order. Let's take a look at the F problem. Right away I see some subtraction. That first part stays as negative 2x squared. I would then, excuse me, let me make sure I change my subtraction to addition there to negative 1. Now I'm going to reorganize here. I'm going to actually take my negative 2x squared and put it with my plus x squared, which you remember is plus 1x squared, same thing. Then I'm going to take these two pieces, the plus 5 and the plus negative 1, and put those over here. So I got my plus 5 and plus negative 1 right here. Put these two together because they are the same. If you looked at the algebra tiles, they would be those squares. So I have negative 2x squared and I have a 1x squared. When I put those together, that's literally just adding my negative 2 plus 1. That's a negative 1x squared. Then my single units, plus 5 and plus negative 1, I would put that together to make a plus 4. So the final answer, they never put the 1 in front of the x, so there will be negative x squared plus 4. Last example. It says use a polynomial to represent problems. In this case, they're using geometry. Use a polynomial to represent the perimeter of the figure at the right. Take a look at the figure. You got to understand what perimeter is first, though. It's a triangle, obviously. It looks like it's an isosceles triangle, meaning 2 sides are the same length. Now, the perimeter of any figure is just the distance around. So if we were to walk around, if you see my dot that I'm drawing, if I were to walk all the way around this, how far would I walk? Well, I'd walk 2y inches plus another 2y inches plus 5 inches. You might have asked, why did you go this way, but then start back up here and start walking this way? Well, I already know. I can see my 2y, I have to add another 2y, and I have to add my 5. And I know that I'm going to put these together, so I'm saving myself some time. Hopefully you see that in your head too. So I just have to add my 2y's and my 2y's. When I put 2y and plus 2y, that's 4y's total. And then plus 5. Can I put that with 4y plus 5? Or excuse me, I can't put the 5 plus with the 4y because this one doesn't have a y. The 5 is by itself. It's a constant. So it doesn't have a y. So I just can put these together, not the others. There's your final answer, actually. You started with 3 terms, you ended with 2 terms. That is the distance around that figure written with the algebra. Don't forget, guys, you can always go back and rewatch the video, read the examples in the book, or, of course, look at the personal tutor and the online textbook. This has been a Friday Shoes production.